So we'll start with the following theorem. We take a non-empty subset S of Rn. Now, affine hull of S, that will be equal to singleton M plus the subspace spanned by the set cap S minus S. And this can be any member of affine hull of S for any M in affine hull of S. But the relation of this theorem to the introduction of an affine combination of finitely many vectors as the counterpart of linear and convex linear combinations is not clear at first glance, but it will be this theorem which will do the job. We will get as a corollary to this theorem the desired result. Proof. Now let us first take M and S. Show this equality to hold when M is a member of cap S, but then it will be an easy job to extend it to this equality holding for any M in affine hull of S. Okay, now first assume that we take some M in S. Now, let us show that this holds when M is in cap S. Now, S is contained in affine hull of S by definition, because all affine subspaces whose intersection is equal to this, they all contain S. So S minus S, that will be contained in affine hull of S minus affine hull of S. Now, what do we know about affine hull of S minus affine hull of S? We know that affine hull of S is an affine subspace of Rn, but whenever cap M is an affine subspace of Rn, then cap M minus cap M, that's a subspace of Rn. As affine hull of S is an affine subspace of Rn, we have that affine hull of S minus affine hull of S is a subspace of Rn. But if this is a subspace containing S minus S, how is this subspace related to to the subspace spanned by S minus S. Span S minus S, that's the smallest subspace containing S minus S. Well, this is another subspace which contains this. Thus, span S minus S will be contained in here. Then, span S minus S, that's contained in affine hollow S minus affine hollow S, so that if I add M to both sides, singleton M plus span S minus S is contained in singleton M plus affine hollow S minus affine hollow S. But what do we know about this right-hand set? M is in S, thus M is in affine hollow S. And affine hollow S is a affine subspace. We know that this is equal to affine hollow S. Okay? So we have shown 1/2 of this equality, namely that the right-hand set here is contained in the left-hand set. Now let's do the converse as well. First, note that what can we tell about this set? Span S minus S, that's a subspace of Rn. So this isn't a affine subspace of Rn. It's just a singleton plus some subspace. But then, remembering what the definition of the affine hollow S is, if we show that this affine subspace of Rn contains the set cap S, then affine hollow S will turn out to be contained in here, as affine hollow S is the smallest affine subspace containing cap S. This is another subspace containing cap S, thus affine hollow S will be contained in here. Now, to show that, S is contained in M plus span S minus S, take any X in S. But then, X is M plus X minus M. But this is in singleton M plus X and M are both in cap S. This is not the first time when we use that we have chosen M in S. So this is in M plus S minus S, but this then is contained in M plus span S minus S. So, S is contained in M plus span S minus S, implying that affine Hall of S is contained in M plus span S minus S. So, affine Hall of S is equal to M plus span S minus S whenever M is in S. Now, the only thing which remains to be shown is that equality continues to hold when M is not necessarily in S, but in affine Hall of S. But what does this mean? But then, the subspace associated with this affine subspace of Rn is, on the one hand, affine Hall of S minus affine Hall of S that we know to hold for all affine subspaces. But on the other hand, it's span S minus S. So, for any M prime, say, to distinguish from that, M prime in affine Hall of S, we have M prime plus affine Hall of S minus affine Hall of S. That's equal to M prime plus span S minus S. But this, as affine Hall of S is an affine subspace, this is equal to affine Hall of S. In fact, for any affine subspace cap M, whenever M prime is a member of cap M, M prime plus cap M minus cap M is just cap M itself. So we have this. So that actually completes the proof of this. Now, we'll have a repetition of two notions, that of a linear combination and that of a convex combination. But what will be new in this definition will be the definition of an affine combination of finitely many vectors. Now, let x1 up to xl for some l, let these be n vectors, and let us take alpha 1, alpha l as real numbers. Now, the combination of the xi's with coefficients alpha I from 1 to L. Well, we refer to this. This is called a linear combination of the xi's. It's called a linear combination of x1 to xl. This is called a convex combination of x1 to xl if, in addition to these being n vectors and these being real numbers, we have for all I in 1 to L, alpha I should be positive, and the sum of the alpha i's, I from 1 to L, that should be 1. Intermediately, this is called an affine combination of x1 to xl if here we have no additional condition. Here we have the non-negativity and the sum being equal to 1. Guess what we'll have here? Just the coefficients adding up to 1, not necessarily non-negative. Now, we'll have the expected corollary to this theorem. Corollary. Again, we take a non-empty subset S of Rn. Now, and well, let's take y in Rn. Now, y is in the affine Hallowes if and only if y is an affine combination of finitely many members from S. Y is in the subspace spanned by S if and only if Y is a linear combination of finitely many members in cap S. Y is a member of the convex Hallowes if and only if it is a convex combination of finitely many members from S, and we have this for the affine Hall and affine combination. Now let's prove this. Well, let's start by assuming that Y is in the affine Hallowes. But what do we know about affine Hallowes by the preceding theorem? By the above theorem. Well, then Y is in here. But But that means y is this m, okay, for any m in S. Well, it's for any m in affine Halabes, but we can take some m in S, well, that will be in affine Halabes as well, and this will hold. Okay? Well, that means y can be written as m plus something from here. Then y is equal to m plus w for some w in span S minus S. But what do we know? Then W is a linear combination of finitely many members from the set cap S minus cap S. Well, then there exist say U1, UL, V1, VL in S, and alpha 1, alpha L in R, such that W is equal to alpha I, Ui minus Vi, I from 1 to L. That is y is equal to m plus alpha I, Ui minus Vi, I from 1 to L, where m U1 up to UL, V1 up to VL, they are all in S. There are 2L plus 1 members here. This is a linear combination of 2L plus 1 members, all of which are in S. With the coefficients adding up to, what's the coefficient of n? It's 1. What is the sum of the coefficients of the u sub i's? That is equal to alpha I from 1 to L, and the sum of the coefficients of the v sub i's, that's minus alpha I from 1 to L, which is 1. So y is an affine combination of m u1 ul v1 vl, all of which are in S. Now, let us also show the converse. Now, conversely, assume that y is an affine combination of finitely many members from S. Conversely, assume that Y is an affine combination of finitely many members from S, that is, Y is equal to alpha I, xi, I from 1 to L for some x1, xl in S, alpha 1, alpha L in R with these alpha i's, I from 1 to L, adding up to 1. This is what it means that Y is an affine combination of finitely many members from cap S. Now, we'll distinguish between two cases. Here, of course, L could be 1 as well. When L is 1, we have Y is, well, that's a one-term sum, alpha 1 times x1, but then alpha 1, that should be 1 in order to satisfy this. Then this will be 1 times x1, which is x1, but x1 is S, and that's clearly in affine Half S. In that case, Y will be in affine Half S. That's what we are trying to show. Now assume that L is larger than 1. Now, of course, we should be utilizing this condition here as well. Now let me rewrite it as follows. This Y equal to alpha 1 x1 plus alpha L minus 1 x L minus 1 plus, now I can write the coefficient of xl in terms of this alpha 1 up to alpha L minus 1. It will be 1 minus the sum of alpha i's, I from 1 to L minus 1, xl. Okay. But then, this simply will be, you'll have xl here, then plus alpha 1 x1 minus xl. Because you'll have here alpha 1 minus alpha 1 xl as well, if you expand this summation. Plus alpha 2 x2 minus xl plus up to alpha L minus 1, this times xl minus 1 xl. What do we know about these? These are all in S minus S. But then this is a linear combination of finitely many members from the set cap S minus cap S. So this is in the span of S minus S. So this belongs to this whole thing. We have here singleton XL plus span S minus S. But this XL is in S, thus in affine Hull of S. This is equal to affine Hull of S by the above theorem. But that completes the proof, because here we have assumed that Y is an affine combination of finitely many members from cap S, and we have shown that Y is a member of affine Hull of S. Any questions so far? Okay. Now this takes us to the last piece in this section. Well, we have gone through this several times. If you have the real line, it's one-dimensional. A point is an affine subspace of R. It's zero-dimensional because it's that point singleton itself plus the subspace consisting of zero only that has dimension zero. But a point separates the line into two parts. If you have a plane, a point does not separate it, but a line does. But a line, that's a one-dimensional affine subspace of R2. Well, again, one less than the dimension of the entire space. Well, next, we have in R3, neither a line nor a point separates the space. What separates it is a plane, which is a two-dimensional affine subspace. Again, 2 is 1 less than 3. Now, what we expect is that n minus 1 dimensional affine subspaces of Rn are expected to possess that separating property in Rn. So we will refer to such affine subspaces as hyperplanes in Rn. Let me first define that. Now let n be a positive integer, a natural number, and n minus 1 dimensional affine subspace of Rn is called a hyperplane. And Rn. Well, if we leave it at this, well then a hyperplane will be a singleton from the affine subspace plus some n minus 1 dimensional subspace of Rn. But let's get back to analytic geometry again. How do we represent a line in the plane? Well, we take ax plus by and set this equal to d. And we consider the set of all points x, y in R2 such that this is satisfied where a, b, d are all real numbers. Now, will this set of points, will that represent a line in R2 no matter what AB are? Is that the case? Now, if A and B are both 0, well, no matter what xy in R2 you take, this will be 0. So there will be two possibilities. If D is different than 0, this will represent the empty set. If D is equal to 0, this will represent the entire plane R2, but not a line. With AB different than 0, 0. Line. What's the counterpart for this in three-dimensional space for a plane? Well, that's the reason why we use here D rather than C. Now we'll have x, y, z in R3 such that ax plus by plus cz is equal to D, where A, B, C, D are in R. But again, if A, B, C are all 0, then this will either be the empty set if D is different than 0, or the entire R3 if D is 0, with A, B, C different than 0, 0, 0. In fact, we can write the counterpart of this. This is plane for point as well. Here you have such that AX is equal to D, where A is in R with A different than 0. Well, here, if A is different than 0, this is a one-element set, which is X is equal to D over A. But if A is 0, this is either the empty set or the entire R. So that's the point. Now, can we generalize this kind of representation of point line plane in R, in R2, in R3, to represent a hyperplane in Rn? Because a point is a hyperplane in R, according to this definition. A line is a hyperplane in R2, and a plane, a hyperplane in R3. Now, this is nothing but the inner product of AB with xy. This is the inner product of ABC with xyz. This is the inner product of A with x. But here the inner product in the one-dimensional case and the usual product and the scalar product, they all coincide. Moreover, if we again go back to analytic geometry, this represents what? In relation to the line represented by that equation, is a normal vector to the line. Okay? If you draw the line, and if you draw the vector AB, that will be normal, orthogonal to the line. Here, again, from analytic geometry, we know ABC, in case this is a plane, that is, this is different than the zero vector in R3, that will be a normal vector to the plane. So the question then is the following. Well, let me write that as a theorem first. Let M be in Rn. Now, M is a hyperplane in Rn if and only if, that is, by definition, this means an n-1 dimensional affine subspace of Rn, if and only if there exists. Here we have two items, a vector and a number. A vector in Rn, but different than the zero vector of Rn, and a real number R, such that M is equal to the set X in Rn with H dot X equal to R. This will turn out to hold, and it's the generalization of this. And this representation actually will have the following big advantage over representing a hyperplane as just an n-1 dimensional affine subspace. Now, in R2, this separates these into two parts, but if you have this representation, then one half space that will consist of those xy's such that this is larger than or equal to t, while the other will consist where this is less than or equal to. Well, here, this and this may interchange. That depends upon what you take as AB, because AB, well, if you take any non-zero scalar multiple of that, that will be a normal vector as well. So that will, okay. We'll prove this. We will need some basic facts from linear algebra. I will first remind you of those, then we will prove this, and we will utilize this phenomenon very extensively, very heavily when we consider separation theorems at the beginning of next semester. Now, after having finished this, now that will be the end of the topics covered in this semester. Then we'll discuss in details in the remaining time of the midterm exam. And then, well, in the last hour, in half an hour or so, we will have an overview of what we have done this semester in mathematics and what we are ready now to do in the future, next semester. Now, since this last section that has examples in the exercise set, but considering this or anything we have done before, if you, well, you will get written solutions to the midterm exam, but if you wish to have written solutions to exercises in this or any other topic, or to homeworks or anything, please let me know. But let me know some reasonable time before the final exam, so I will have time to prepare and to send them to you. Okay? So we'll have three hours left. The proof of this will take 1 hour. Then in the remaining hour and sometime from the last hour next week, we'll discuss the exam questions, and then we'll close with the overview. Okay? So